Today it is my extreme pleasure to introduce our speaker. Well, first let me step back. I'm Lisa Goldberg, and welcome to this week's CDAR seminar. I'm one of CDAR's co-directors, and it's my extreme pleasure to introduce our speaker, Ruimeng, who is a professor at UC Santa Barbara in the Department of Statistics and Applied Probability. So we have, I don't know if you know Ruimeng, but we have a lot of connections to your department, many friends there and many topics. So really great of you to join us today and present. Super excited about the subject, directed chain generative adversarial networks. Wow, it's a mouthful for multimodal distributed financial data. So before I turn over to you a question, do you prefer questions interrupted during the presentation, or do you want us to hold off to the end?
I would prefer the formal one. Yeah, we can have a during the talk. Yeah, that would be great.
So we'll all stay muted, but unmute and jump in from time to time. Please go ahead and.
Sure. Well, thank you, Lisa, for this very nice invitation and also for the introduction. Yeah, as she introduced, I'm going to talk about a generative framework for modeling multimodal distributed financial data. Okay, and so let me start with, so the work I present today will be based on collaboration with Ming, a former UCSB student, and also Tomoki Ichiba from the same PSTAT department at UCSB. And below are the main references. The first one is the main topic that I'm going to cover today, and if time permits, I will also talk about another applications of signature in machine learning or in deep learning. And then the last one is like the theoretical foundation of this directed chain stochastic differential equations. Okay, so let me start with some motivation or observation from the from real world data. So we take some example from the Google data and from this Yahoo Finance. And those are some daily data. We look at their high value or low or opening prices, close prices. And if we plot it and using this histogram, then we naturally can see there's a multi-modality feature. So multi-modality means that in the distribution, you have more than one peak in your densities. And another example that later we will also use in our experiments is this airline energy as consumption. So this probably make more sense, as you could imagine, the utility usage usually has some fluctuations. There's a peak time, there's a off-peak time. During the peak time, there's a natural very high usage, like usually from like 4 p.m. to 9 p.m. And then there's an off-peak time where everybody go to work, and then there's usually barely no utility as consumption at your house. And so those naturally will give some of your peaks of this of your histogram or the distribution of your consumption.
Okay. And I interrupt Ruimeng with a question right away. What are the dates, especially on the Google one, so I can have some context on?
So first of all, the x-axis is rescaled for daily, and then we rescale it from 0 to 1, and I believe we are taking like from 2004 to 2019 years of data. It's before the pandemic. Yeah.
So so there's quite a few financial regimes.
Yeah, exactly. So it's better maybe to use a shorter regime because usually financial data are non-stationary. Yeah.
Right.
Yeah.
Got it. And one more question, and I work with financial data a lot. Any reason why you pick prices instead of returns?
That's a good point. The reason is that I mean, in the other previous work on generated time series data, they're all using this high price or low price from the Yahoo, and then we are trying to make comparable results with them. So we are following this regime. Yeah, but I agree. I think the return could be a better like data as a serve as a data. Yeah,
it would be different, but it would also show regimes, of course.
Yeah, I agree.
Okay, thank you.
Yeah, I would just like to mention that there are statistical tests for multimodality, and it would be helpful to just see some of those to provide a quantitative backup confirmation of the eyeballing conclusion that these are clearly multimodal distributions.
I see. Yeah. Oh, thank you for letting me know this. Yeah. To be honest, for parts of my research are more on stochastic control problems and games, and this is one of the very few attempt that I'm trying to make into the data generation or data analysis. So I would say I'm pretty new in playing with data. So I really appreciate those comments. Yeah. So let me continue here. We sometimes the data sequence can also be irregular sampling, meaning that if you look at the timestamp between the two data point, these timestamps are not equally spaced. And then also the time series data sometimes have the non-Markovian features, like the usage, like 1 hour, the usage, the utility consumption right now may be highly related to the consumption like 1 hour ago. Okay, and so what are the framework? Well, what are we trying to employ in order to generate this multimodal time series data? So we're going to use this GAN, the generative adversarial neural networks. So those are very popular already in the machine learning field, and I guess right now everybody are very familiar with it. But just to give a brief introduction. So it starts from generating like fake faces from real faces. So the GAN framework consists of like 2 neural networks. One is called the generator, the other one is called the discriminator. So the generators usually will map the noise, the white noise, into some fake data. And in this particular application, they will map those noises into fake faces. And the generator will try its best to fool the discriminator by maximizing its own like parameters of the neural network. And the discriminator's job is try to distinguish between the real faces versus the fake faces. So he will be given 2 sets of data. Those real faces are labeled with real, and then the fake faces will label with fake, and then he will try to maximize the discrepancy, the score between these 2 sets of data. So it's kind of a game between the two parts. The generator is trying its best to fool the discriminator, and the discriminator is trying its best to distinguish, to tell apart the real ones from the fake ones. Okay, and for this particular example, again, it's used to generate like a one-shot object, like a picture at one time. And later on, there are also some work on generating time series. But I will show why those are not capable of generating like multimodal time series. But before that, let me explain why like this net generative models are important. So the first reason we think is due to this data scarcity. So we all know that the financial data are non-stationary, and so sometimes you won't have enough data to learn to conduct the to conduct the research that you are interested in. And one way is to have a generative model to learn from the limited data and then try to generate the data that has the same distribution as the real data. And the other motivation is actually from clinical trials. So for some medical data, usually you cannot get them due to the privacy issues. And then how would you still try to do some analysis of those data? One way is try to use those medical data to train a generative model to train again, and then you can have the access. You can access this generative neural network and then try to do some analysis or try to analyze the pattern of the data using the data generated from the GAN. And a third reason could be like the cost. For example, if you want to access the high frequency data, usually right now you need to purchase from some data vendor, for example, from Lobster or from Data Bento, and usually they are very expensive. As far as I know, a purchase from Lobster costs probably like $5,000 per year. And if you just want to start with some initial analysis of high frequency data, maybe you want to work with a generator which can are trained based on the high frequency data. Okay, so those are some motivations of why we want some generative models. And then there are indeed some existing work. For example, this time generative adversarial network time GAN, which is based on a auto-encoding component in their generator, and the CTFP, which is continuous time flow process. This is based on the normalizing flow, and neural SDE, which is based on this is a stochastic version of the stochastic of the neural ODE. Sorry, which parameterize the drift and the volatility term of the stochastic differential equation and use it as a generator. And also SIG-Wasserstein GAN, this is based on signature and then Wasserstein GAN. And also the last one is the transformer-based GAN, where the generator has a transformer component in there. So there are already several of them, but by the time that we are doing our work, we search the literature and we try out those existing work, they do not perform well for generating multimodal distributed data. And let me take this neural SDE as an example. So what does neural SDE do? So as all the other, most of the other existing literature, they try to map a noise, a white noise into some as the starting point of their generator. So they start with a white noise, and then they parameterize the drift and then the volatility using some neural network, and then inject the noise into the initial condition, and then try to produce a process using this SDE. And then the output of the generator will be a fine transformation of this SDE, neural SDE. The discriminator will take the generated data and then using this as the integrated process, and it will also parameterize the drift and the volatility using neural net. And then the score of the discriminator is a linear transformation, a fine transformation of the hidden state, of the final hidden state. Okay, so in their framework, this discriminator is followed by this idea called neural CDE, neural controlled differential equation, because they claim that this YT, which is produced by the generator, is like a controlled process. Okay, so we take their framework, we exactly implement using their code, and then try to work on the following example. This is a very simple one-dimensional stochastic opinion dynamics example, and it's one dimension and then characterized by this YT, where YT is it's a Marquin-Vlasov type stochastic differential equation. So the interpretation is YT is like the level of an opinion, and then you are updating your opinion by averaging the neighborhood, your neighbor's opinion, where this phi is like opinion kernel or the interaction kernel here. So if we look at the picture, then there are two histograms in each panel, and they are by blue and then by red. The blue one are the data generated by this model, by the stochastic opinion model, and then we start with some uniform distribution. And then as time evolves, you can see that the opinion diverges into like two peaks, especially here and here. And then in the end, if we let the time to run sufficiently long, then the opinion will converge in the end. Okay, so we take those generated data from this blue equation as our real data, and then we try to see if the neural SDE framework can fully capture this evolution of the opinion dynamics. And the answer is unfortunately no. It is trying to capture this multiple peak in the distribution, but it fails to do so. Okay. And then later on, we can show some picture of our framework of a DC-GAN, which can effectively capture this divergence in the opinions and then the convergence in the end.
Can I ask another question? Just I'm super excited to see yours, but if I were to take this type of framework and you put in something other than a Brownian motion, a different, would I have a better chance at capturing those peaks or no?
You mean in this neural SDE framework, replacing?
Yeah, if I were to use some wilder form of uncertainty, just what they're doing, do you have any sense of whether that would help?
Maybe for some asymmetric type of noise, it could be better. Maybe,
Okay.
yeah.
It would just, I've always tried,
Yeah.
trying to think of how to fix this up, but you probably have a better way.
Yeah. So the intuition we have is that, well, I think the reason that it cannot fully capture is because you are mapping the noise, the white noise, which is a symmetric distribution, and it's a unimodal distribution, and you are trying to do some transformation to make it into a multimodal distribution, which is really hard.
Right.
Yeah.
But if I were to do something like really dumb, like taking a two-state process with transition probabilities, I can get multimodal data out of that. It doesn't look anything like I need it to look, but I can create, there's lots of things that I can do to create those peaks, maybe not in a very satisfying way.
Yeah. I haven't, I can only say that I haven't tried that approach as using like maybe a Markov chain or a Markov process with like two states and then using some transitional probability. I haven't tried that. Yeah, but I think that was trying. Yeah.
Okay, thanks.
Yeah.
So I'd like to follow up on that. So I've got a naive question. So if I have a random number generator that generates uniform distribution over 0, 1, I can convert it to generate a random number generator with any distribution I like by just mapping the cumulative distribution function from the uniform to whatever I want. So, I mean, so I think given any unimodal distribution, I've got some function will take a conventional random number generator and produce that. So there must be some constraint on what's an allowable form of generation in order for, for this problem to be well posed, right? I mean, so Lisa was sort of getting at the same thing, but I'm asking at a more fundamental level. I mean, suppose, I've got a bimodal distribution, anything you like. Well, I can, take the transformation function from the CDF of a uniform that maps into that, and then I've got it. Now, of course, in order to do that, I need to know what the two distributions are. So maybe that's the issue. But I guess I'm still a little bit unclear about what constraints are underlying this process, so that one way of dealing with this is considered okay, and another way is considered not because it requires too much information or something like that.
Yeah, I agree. Yeah, I think that's a very, very important question. And so why this? Why, as you said, there's approach to invert the uniform distribution into bimodal distribution, and so what prevents such a neural network framework to fail? Right, to be successful for in generative. Yeah, so we try to think about the underlying the reasoning behind it. I mean, we didn't have a very solid mathematical explanation. The only thing that we have right now is that we observe such a phenomenon, and it is actually widely documented in the machine learning field, that such transformations starting from the Gaussian white noise are usually not capable of capture multimodality. Yeah. So the problem exists in a while already, but we haven't have some like good explanation on that. Yeah.
So this is a stochastic process. So there's a time dimension. Are you trying to characterize the paths of the process, or just the values of the process at a fixed time? So maybe that's what the issue is.
So those plots are at different time of the process. So at each time you have a distribution, right? And then if I look at distribution, then the one generated by this blue equation is multimodal. You have multiple peaks there at some point. Yeah. Okay.
So maybe that's an answer, or part of the answer. Okay, thank you.
Well, thank you for the question. Yeah. So let me continue. So for us, we are now trying to start with a white noise. So what we are doing is based on this called directed chain SDEs, directed chain stochastic differential equation. So the solution for the directed chain SDE consists of the two processes, X and X tilde. So they are a pair of square integrable processes while satisfying this stochastic differential equations. And there's an additional constraint, distributional constraint, which will require the law of X to be the same as the law of X tilde. Okay. So this is a model that proposed by Ditorin Fouque and Ichiba in 2020, and then this paper is called Directed Chain SD. And in there, they are able to prove that under proper conditions of V0, V1, let's say ellipsis conditions and linear growth in linear growth, the system has a unique weak solution. And the unique is unique in law. Okay, and the motivation for such a directed chain SDE is from the uncoupled SDE system. So in the original paper, they start with a uncoupled SDE where X1 will depend on X2, X2 depend on X3, X3 depend on X4, etc., until Xn depend on X1. So they will have this like circular structure in this uncoupled SDE system, and then by letting n goes to infinity, this circular structure will be will no longer exist, and then it's like a chain structure which is shown in the plot B here. Okay, and then later on we will also try to use this chain structure and then to improve our framework for generating multimodal data. Okay. So how are we going to use such a SDE to develop our generator? So let me start with the next slide. So given that we have those distribution constraints, so recall that this is like a normal SDE, but you have a additional constraint where you require the law of them to be the same. So the natural idea is trying to say, oh, I'm going to use one of the object to be my real data, and then the other one as my generated data. So this is exactly our methodology. So assuming that now we know the function form of V0 and V1, then we can try to plug in the real data into this X tilde, and then use the knowledge for my V0, V1, and then having some Brownian noise to generate my X, and then view this generated X to be my fake data or the output of my generator. Okay, so we are going to follow this idea, and then later on we're going to call this X tilde to be the neighborhood process. And so our approach that distinguishes from the rest of the literature is that we directly learn from the real data. So our generator will take this X tilde, take the real data as input, while other generators are usually just maps the Brownian motion into some arbitrary time series. Okay, and but by utilizing such a idea, there are two issues. The first one is, at the moment, given a data set, we do not know whether they are following such SDE, and more importantly, we do not know the form of V0 and V1. Okay. And then the second issue is that if we are using such a methodology, we plug in X tilde to generate X, and there will be only limited generating power. So I will explain what this means in a few seconds. Okay, so let me explain how to address the first issue first. Okay, so the first issue is that we do not know V0 and V1 from a given data set. And as I'm doing this GAN framework, I'm of course going to parameterize them using some neural networks. So I'm going to replace this VI by the VI theta, where the theta will summarize all the parameters from the neural network. And then I can generate X using the X tilde, which I'm going to plug in the real data. And then VI theta, which is my parameterization of those unknown functions and some Euler scheme, for example. And then how to determine the optimal weights for this theta? I'm going to determine the theta by enforcing the law of my generated data to be the same as to coincide with the law of the real data. And this is where the discriminator came into play. So the discriminator will try will try to maximize the distance between these two, and the generator will try to minimize the distance between these two laws. And in particular, when we are doing when we are designing the discriminator, we'll use the signature versus tangent and also the neural CDE. The neural CDE is already been employed in the neural SDE paper, and I think I showed it in a previous plot. So let me take a closer look of the sig versus tangent. So the sig versus tangent, the first equation that will be based on a object called signature. This is a concept in the route path theory. So given a process, we can define a infinite sequence where xk is the kth signature. This is the kth iterated integral of the your given process. And then this is an infinite sequence. If in reality we want to use algorithm to implement it, we always need to truncate at a certain order. So Sm will denote the truncated signature of X of the depth M. So it will contain the first M+1 component of the signature, and it has this dimension. Okay. And why a signature is important or is useful in generating time series? There are multiple reasons. For example, it can encode this temporal information regardless of the sampling frequency and the variable length. So no matter how long the sequence is, we are able to define the signature, and it has the universality property and also factorial decay. Factorial decay means that if I only use the first M signature from this path, and then the remaining the information remained that are left to be captured is 1 over M factorial. So by using the first several objects into the signature, you already summarize a lot of the information from this path, and this is a very, very useful definition or a very useful concept when when trying to measure the distance between two processes as proposed in this sig versus tangent. Okay. And the other, I think I've already showed this picture before, where in the neural SDE framework, they are using the neural CDE, the control differential equation, to construct their discriminator, where basically they take the generative path as the integrator of the second SDE, and then do a linear transformation and then take it as the score of the discriminator. So that already addressed the first issue, which is how that we are not knowing the V0 and V1 and how we address it. The second issue is about independence. So for being again, you need to have certain properties. For example, you can generate it can generate independent samples, and it can generate as much as samples as you want. So those are the features that again must have, right? And if you are starting from a white noise, some independent Brownian motions, then of course, every time you plug in a new Brownian motion, a new independent white noise, then the output of your generator will be independent. But for us here, since we are plugging our data as part of our generating process, so we cannot guarantee that such independence will still there. So we need to take some method try to prevent the correlation between the input data, between the real data and the generated data. And then the way we are doing it is the following. So we call this to be a walk along the chain. So we take the X tilde or the real data as the X tilde, and then we take the already trained neural network VI, and then try to generate some sequence of time series. We call this to be the X1, okay? And now we view X1 as the new X tilde. So we plug in what we have X1 into the place of X tilde, and then we use this VI star to generate X2. Okay, now we take X2, which is the generated data already after the second time, but we plug this information into X tilde, and then we generate X3 until we do it, we repeat it Q times. Okay, and we call this to be walk along the chain for Q times. Okay, and then we in the paper we show that after we walk along enough steps, then the training data, the correlation between the training data and the generated data can decay exponentially fast. Okay, so that serves as a theoretical guarantee that if we take Q to be large enough in the experiment, we take Q to be 10, then the XQ, XQ is almost independent from X1, or XQ is almost independent from the real data that we are taking at the beginning. Okay, but by working along the chain one time, we can only generate one set of fake data, which has the same size of the real data. So how to generate more data? We just take more new independent Brownian motions, and then to work along the chain one more time, and then there will be another set of generated data, which naturally XQ1 will be independent, has less correlation, very small correlation with X1, and then XQ will has very small correlation with X1, etc., etc.
Sorry, I think I missed something, but there's an arrow from X1 to X21. Mm-hmm. Does that just indicate that the generating process is based on X1?
I think I should write this to be X tilde. Yeah. So everything starts from the real data. You think about this X to be the real data.
Okay.
Yeah.
Okay.
And then you go to X2, which is the first time you got the fake data from the generator.
Right.
And then you view X2 as the real data, and then you generate X3.
Right.
And you keep going. Yeah. Yeah. Sorry for the confusion this time. This notation inconsistency. And then you keep going for another chain, and then that gives you another set of generated data, which has a very little correlation with the real data. Okay.
Thank you.
Thank you. Good. And each set can serve as a nearly independent data, which is obtained from the generator. Okay, so we believe that by taking these two, this approach, working along the chain and working many times, we will fulfill the goal of being a generator, which is that it has to generate independent data and has to be able to generate as much data as they can. Okay. So far we've already, I hope I convinced you that we can address this issue that I mentioned before. And then now let me show some experiments. In this paper, we take 4 experiments. We have 2 synthetic data and 2 financial data. So to measure, to showcase or to measure how good the generator is, we have several metrics. The first one is the marginal distribution, or this called maximum mean discrepancy. This is by like plotting the histogram between the real data and the fake data, and also by computing the MMD. Okay, and then there are other metrics. For example, this is the discriminative metric. So a discriminative metric is you train a 2-layer LSTM discriminator after you train all this generator, after we train all the GAN framework. And this discriminator is trying to tell whether a data is from our generator or it's from the real data set. And the philosophy here is that the worse the discriminative ability, the better our generator is. So this discriminator is not the discriminator that I showed before by using the Wasserstein GAN or by using the NeuroCity. This is an additional one, which is after the whole training of the DC-GAN. So this is something post hoc. Okay, so we are trying to say that our generator is really good, and you cannot really tell by using a third party like Judger. Okay, and another metric is this predictive metric. So this is another 2-layer LSTM neural network, and it is this LSTM predictor is trained using the generated data. And the philosophy is, if my generator can fully capture the distribution or the evolution in time of the real data, then if I'm using the generated data to train this predictor, the predictor can perform well on the real data. By performing well, I mean after the training of the predictor data, I input the real data into the predictor and let it to predict the next step. And if the next step has a very small distance with the real data in the next step, then I think I'm good. So now here is the smaller the distance, the better the generator. Okay. And another, the last metric that we also concern is the independence metric, which between the processes, basically we are taking the supreme norm over all the time, and then to try to compute the correlation between the time series at each step, at each time step. Okay, and then for this experiment, we are comparing with other state-of-the-art work. The things that we consider here is the Wasserstein GAN. This is proposed by Ni Hao and her co-authors in 2021. The CTFP, continuous time flow process in 2020. The Neuro SDE in 2021, time GAN, and then the transformer-based time series GANs. So those are the ones that were proposed recently, and also trying to generate time series. And we take their original code from GitHub and implement into our data set. And then we have the following like plots and then tables I will show. Okay, so the first example, we already see it in the at the very beginning of the talk. This is the stochastic opinion dynamics. It's a one-dimensional thing. YT characterize the opinion of a representative, like a player or agent, and then he's trying to update his philosophy or his opinion of a certain topic based on such a dynamics. So he's trying to average his opinion versus the average of his neighbors, and then to keep going forward. And then there's some stochastic noise in the end. Okay, the phi here is called the interaction kernel, where theta 2 characterize the how large the neighborhood you are considering about, and the theta 1 is like the strength of your of influence from your neighbors. Okay, So you have seen already the first row of the plots. They are produced by the neural SDs, in particular the red ones. We can see that although we train hard on those neural nets, it's incapable of capture those by peaks. It can produce multi-modal distribution, but it just cannot fully capture the true distribution from the data. Instead, for us, we take the DC-GAN approach, the directed chain generative adversarial networks, and then our generated data, which is the red histogram in the second row of the plots. It clearly has this a uniform distribution, and then diverge into 2 peaks, and then into higher 2 peaks, and then in the end it converge into like a almost a unimodal distribution. Yeah. So I mean, from an eyeball perspective, I think we are doing better than the neural SD, and we are capture like there's a good sign of capture this bimodal distribution. Although I agree here there's some like discrepancy between the red and the blue one. Yeah, we are trying to improve it, but still not still in the progress of this part. Okay. And then so this is only this is about the plots from the metric that I mentioned at the beginning. We run the experiments, I think 10 times, and then we take the average as the numbers in those columns, and then the numbers in the parentheses are the standard deviation from the multiple runs. And from this table, we are able to see that comparing with other methods, DC-GAN performs the best. So it has the smallest discriminative score, meaning that the data generated by the DC-GAN cannot be distinguished or by the 2-layer LSTM discriminator that we trained post hoc. And if we look at the MMD, which is the maximum mean discrepancy between the distributions, then this is also the number is also very small. And then the independent score, which measure the correlation between the generated data versus the real data, then this score, you will see this is very small, and it's comparable with other methodologies, where for other methodologies, they are supposed to generate independent samples. So if their independent score are of the same level, then we believe that our samples are already like has very little in correlation from the real data. And also we have a very comparable running time comparing to the existing method. And so just to illustrate, if we are not working along the chain, we are just using X1 instead of doing this X1, X2, and XQ, then the independent score will be much higher. So that really means that we have to go along this process, and then to reduce the correlation from the original data. Okay. And then we have more models. The second one is also from a system of stochastic differential equation. This is called a stochastic Fitzhugh-Nagumo model. So this is a model try to characterize the activation and the deactivation of the neurons. And it's high dimension. We try to plot the histogram from like certain 2 dimensions, and you can see exactly clearly that there's a bi-peak in their distribution. And again, we highlight our experiments scores, and then it has comparable independent score from other framework, but we have a better MMD and discriminative score. Okay, and we also have a comparable running time. And there are 2 more experiments which are based on real data, and the first one is on the Google stock data. For here, we as Lisa asked why we are now using the return. Yeah, the real reason is that for other experiments in the past, they are using those channels from a certain stock. So we are just following this history and then try to compare with their results. And I think it was investigating into taking the return or having a smaller time of the frame, and then to see if such multimodal distribution still exists, and if our framework can also perform well in such a data set. So here we are taking this volume, high, low, opening, close, and adjusting adjusted close prices. And then we by plotting the data, we notice that the first 5 channels are multimodal. And if we compare our algorithm with the existing ones, we still have can reach the same conclusion. We have a very comparable independent score from others, which are the rest of the framework are supposed to generate independent samples, but we have a very good MMD, where that means our generated distribution are very close to the real distribution. And our discriminative score are also very small, which means the data generated from our generator cannot be tell apart. It's hardly to be tell apart from the real data from a third-party discriminator. Okay. And then the last one is from the energy consumption, where we take the data from Ireland, and then there are 4 channels that we think about. They are from the electric and then gas assumption from the from different areas. And then for 3 out of them are multimodal. You can see so if I go back here, so 3 out of the 4 channels are basically plotted in this way. So there's like a seasonal peak, or like within a day. So within some hours you have a very high consumption, and then during the middle of the day, usually people are not at home and there's no utility consumption at all. And then during the night, when people go back home, and there's a high peak. Yeah. And so this is the last table I'm going to show here. In this experiment, we also try to compare different discriminator. So one is the neural control differential equation, and the other one is the signature Wasserstein-GAN. And then combined with our generator, which is from the DC-SD. So the Wasserstein-GAN really outperform among all of them. And so we believe that signature is really a good tool in terms of generating time series and also measuring the distance between time series. Yeah. So this is the experimental part. So now let's talk about some theoretical guarantee. So the first thing that we try to convince people is that when we are using the directed chain SDE, what is the are we losing any expressiveness if we were using the neural SDE? So the neural SDE are basically trying to parameterize mu and sigma using neural network, and then generated the data using such a parameterized stochastic differential equation. And in our case, we are using this framework. Okay, and then so we are able to show that at least X can has the same marginal distribution as Y, and this is done by obtaining the forward homograph equation for such a DC-SDE system. And this is such a system was derived in a previous paper by Tomoyoki and Ming in 2022. And then we compare this forward homograph equations with the ones for the Y, and then we are able to identify the V0 and V1 so that they will have the same distribution. So by using such a SDE for generation, we are not losing anything. And actually, I believe we can express more exotic distribution. Yeah, but this is just a intuitive thoughts from our experiments. Yeah. And then the second one is the conditional exponential decay property, which plays the theoretical foundation of working along the chain. So if you can still remember, after identifying other V0 and V1, if we are not working along the chain, then there will be a high correlation between the generated data and the real data. And the way we do it is by viewing the generated data as the new real data, and then use it to keep generating a fake data. And then we take the step several times. And here, I'm sorry. And here we have a theorem saying that for any like Lipschitz function phi, if we measure the distance, or if we try to measure this distance, the conditional distribution, then after Q steps, this distance will be small in the sense at the order of 1 over Q factorial. Okay, so that means if we are having if we are working along the chain like sufficiently many steps, then we almost have no like correlation between the generated data and then the real data. And then the theorem that we're using here are basically ground volume inequality and then the Lipschitz property, and then trying to do an induction to obtain such a such a estimate. So I think that's pretty much about the DC-GAN, the neural directed chain generative adversarial network. I'm not sure if I still have time, but I would like to pause here and then to see if there's any questions or discussions.
You do have time, Ruimeng, and I have not theory questions, but more general questions. This looks like, would it be fair to say that what you've constructed is like a very flexible random number generator?
It's more the random number generator because we are generating time series. So
right.
we try to capture this time evolution into the
yeah. Okay.
Yeah.
Great.
Yeah.
And then I know, for example, like I have friends working at Tesla Autopilot, and they have told me that the limiting condition on their ability to work is to generate enough data to train the cars on. There's not enough data in the world, and they are trying all the time to make reasonable data for training the autopilot. And I wonder if these ideas have been used in any of the in a practical context like that.
I would be happy to apply this framework into real world problem. Yeah, I'm very interested in that. Yeah, right now I'm not aware of that. This is a new work we published last year. Yeah. So what kind of data that they are interested in, like that they are not capable of generating? So is there a special feature that they are looking for their like autopilot data?
Well, I don't know. Maybe I can. I'm not working for Tesla Autopilot, so I don't know the answer. But I do. It's some place to go that's a little less flashy, where I have a little more grounded. So I have a particular problem, which is we've developed something, never mind what it is, and we developed it on simulated data, and then we tried it out on the real world data we had, and it didn't work very well. And then what we did was we went back and forth between the real world data and simulations, putting in more and more features, right? And now it works very well on real world data. But the thing is so data mined that I don't trust the result. Do you see what I mean? I mean, we use the real world data we had to create simulations with features that we understood. And I'm wondering if this kind of gadget could be helpful to us in creating new challenges for our simulated data. I mean, part of the problem is that you're just mimicking. The problem with all these things is just mimicking what's out there. And what you want to do is to get it to come up with new things that are somehow reasonable and predictive of the future, but that we haven't seen before. I don't think anything can do that, but that would be what you want.
Yes. Yeah, I agree. Well, let me think about it. Let me see.
Well, these are almost philosophical questions. I'm trying to see, maybe we can talk offline and I can try and show you the problem I have.
Sure, I was interested in that. Yeah.
And then after that, once I get to know your stuff better, can try to figure out if it makes sense to connect you up with Tesla Autopilot. But don't understand well enough yet. But I see a use for this and something I know well, or potential use, where I just need more data to test. I mean, all through sciences, right? These empirical studies turn out to be wrong because everybody, often with super good intentions, data mines the thing to death. And it's just all a bunch of in-sample fits labeled out of sample. This is like a terrible problem for science. And getting out of that problem, if you can do anything to get us out of that problem, that's a great thing.
For my understanding, I think generative model, or I feel that generative model work well with data interpolation, but not very well for extrapolation. So if you have a certain data set and you want to learn some feature and then to reproduce the feature, I think again, it's good. It's good. But if you have a data set and you have some feature and you want to the GAN to develop some new features, or I'm not sure if that's capable of GAN. Yeah, that's my feeling. Yeah. But I definitely want to have interest in apply this framework into more like real problems. Yeah. So right now I built this piece of work as a new framework, and then we are taking those experiments, but I feel it's still at the toy model level. And then I hope I can find some like real a practical problem where this framework can be very useful. Yeah.
Well, I have no shortage of practical problems, so no, very easy for me to list them for you. Do you have more you want to say, or do others have questions?
Is there other questions from this part?
All right.
Okay. Maybe a couple of minutes for another application for this signature. So signature is not only very useful in generate like time series data, as it can efficiently capture the time evolution of processes, but it is also a useful like object or concept in solving other like machine learning algorithm. For example, I have another work which try to solve like mean field gain with common noise, and their signature also plays a very, very important role. So I won't go to details for this part. I will just highlight some key components here. So what is a mean field gain? So mean field games are a game between a continuum of players, and they are in a competitive setting. So they try to maximize their reward or minimizing their cost, but they are interacting with the distribution of the whole population. So that's why if I look at this dynamics and the goal of one representative player, then the mu, which is a distribution, involves in the formulation. And then when you have the mean field gain with common noise, that means each individual player do not only face the individual noise, but they also face a common noise, which appears into the dynamics of everyone. So this is like a common shock for the system. For example, in the financial crisis, and then a common shock it will impact all the banks or all individuals. Okay. And then signature is also very useful in solving such a mean field gain with common noise. So what is the solution for mean field gain with common noise? So in obtain solution, that means you need to identify a pair, alpha star and mu star. And if you look at the distribution obtained by alpha star, and this will be a stochastic measure flow mu star, then this mu star will have to coincide with the conditional distribution of the optimal states given the common noise. So this is like a fixed point, and this echoes the Nash equilibrium in the finite player game. So you want to find this pair simultaneously such that the optimal conditional law produced by the optimal strategy coincide with the optimal law that you are using in this formulation. Okay, so where we're going to use the signature, basically, we're going to replace this filtration of the common noise by the signature of the common noise, and then later on by the truncated signature of the common noise. So what we are going to say, what I'm saying is that we are going to use the signature, try to efficiently characterize the conditional distribution, or in our case, try to efficiently characterize the conditional moments. Okay, so those are some like possible ways, but our way is trying to directly parameterize the control that we are going to obtain, and then trying to use signature to present conditional mean field. Okay, so there are some other like technical details. I don't think I'm going to go through everything, but maybe just one quick remarks. So why we are using signature here is because it can characterize the path uniquely up to a tree-like equivalence. So, and it is unique if at least one dimension of the path is strictly increasing. So then in the practice, people are usually concatenate any process with a time dimension so that the first dimension is strictly increasing, and then the whole thing, the signature of the whole thing will be a equivalent, unique characterization of the path itself. And then if we are trying to like express some conditional law or the conditional moments given the filtration of the common noise, then we are going to replace this by the signature of the concatenate processes, and later on in the computational part, we are going to replace it by the truncated signature. And this is guaranteed this by the factorial decay. So by truncating the signature at a certain step, we are not certain depths, we are not losing a lot of information. Okay. And then this is the evolution of the algorithm. I think I'm going to skip it here and then just look at one numerical example. So for this part, we also have some convergence analysis, but just let me show some pictures. So this is a mean field game of optimal consumption and investment. So you can think about a situation that there are many agents. They are trying to do investment in the market, and they are also consuming their wealth. And then their utility are based on how much you consumed comparing to their peers, and how much your terminal wealth is above your peers. So the more you are above your peers, the happier you will be. Okay, and the X here will be your wealth process. You're following this self-financing strategies, and you're invested in a log normal market. The interactions between these agents are through these two parts, where it's the gamma T and MT, where we are comparing the wealth of one single agent versus the average of the rest, and you're comparing the consumption of a single agent versus the average of the rest consumption. Okay, and this problem is actually very hard to solve. This is a extended mean field game with common noise and with heterogeneous agents, because all those theta and delta, those could be like random variables. That means there are agents from different types, and then they subject to a common noise in the system, and then they interact not only through the distribution of the dynamics, but also through the distribution of the control. So this is theoretically, it's already a hard problem to solve, but numerically, because we are using the signature, we can obtain very good results. So those trajectories are actually like two sets of trajectories. You have the dashed line and you have the dot line. The dashed line are the truth, and the dot lines are the simulated solution or the solutions from the numerical experiments, and we are able to show that they are almost on top of each other. So the accuracy is very very good here, and also the utility of this representative agent. We have a analytical solution here, which is about 2.58, and then the numerical part is about like 2.6. So it's only like 2 cents of the true solution. So we believe that such a signature is also very useful in expressing conditional moments and then in solving mean-field game with common noise. So this is like a additional illustration on the signature, the use of the signature. Well, yeah, thank you for the attention. Yeah, thank you for your attention.
Well, thank you for a very thought-provoking subject. So before we thank our speaker, do we have any final questions from this audience?
I have one. First of all, thank you very much for presenting a very impressive and promising method. I think you already partially answered for my question, but my question is that, I'm basically very interested in the, practical limitations of the neural DC-GAN method, where we need to be careful to apply your method in practice. So comparing to other, well-known methodologies, similar methodologies, when we should not use this method, other than the extrapolation issue you mentioned, because it's common. I mean, it's really hard and difficult area where most of the methods are not doing well. So that's my question. What's the potential limitation of the method? Thank you.
You mean a potential limitation for the neural SDE or the potential limitation of our method?
Your method, the DC-GAN method. So my question is when we should not use that method in practice.
Oh, that's a hard question.
Oh, really?
Yeah, the thing that I could think about is the extrapolation, which I think that's a usual issue for the GAN. On top of that, let me think about it. I'm not aware. I would say I'm not aware at this moment, and partially because for this piece of work, we are focusing on multi-modal distributed data, and we can really show that our framework outperform the state of the art. Maybe we can also try to test if such a thing can work on the non-Markovian time series. That's something that we didn't test for the synthetic data set. Yeah. So that I'm not sure. Yeah. So there's something to be tested. Yeah.
Okay. Thank you very much.
No problem. Thanks.
Any further questions? Okay, well, let's thank our speaker. That was really excellent. Can we post the recording and the slides, Ruimeng? And if you have a paper, we can post a link to it?
Sure, yeah. The paper is published in the International Conference of Machine Learning, and I can also share my slides. Yeah.
Great. So we'll follow up about that. I will be following up with questions about some practical problems I know. So this was great. Thank you. Thank you everyone for listening. And just want to mention this time next week, we will be having Aaron Yoon from Northwestern University will be presenting. So please watch the announcements for title and abstract and more information.